Alright guys, this is your notes for 5.3, the binomial distribution. So for a random variable to be considered binomial, or for a distribution to be considered binomial, these four things have to happen. Alright, it has to happen for it to be considered binomial, and for us to use the techniques we're going to talk about in this section. So you have to have a fixed number of trials. What we mean by that is a procedure that is binomial would be something like, I'm going to flip a coin 10 times and I'm going to see how many heads I get. That's binomial because I fixed the number ahead of time to be 10. Alright, for a counter example, something that wouldn't be, I'm going to flip a coin until I get a head. Alright, that's not binomial because I don't know how long it's going to take until I get a head, so I'm not fixing the number ahead of time. Okay, and then the trials must be independent, so the outcome of any individual trial doesn't affect the probabilities of the other trials. So again, with my coin flipping example, if I get a head on the first coin flip, that has nothing to do with what's going to happen on the second or the third or the fourth. Alright, and each trial must have all outcomes classified into two categories. Okay, and you're going to hear us or hear me say success and failure for a lot of things. Now, I could say something like we're considering having a girl as a success, and then that would mean having a boy as a failure. Okay, it doesn't necessarily mean good and bad. It just means the thing that we were looking for is our success, and the thing that we weren't looking for is our failure. All right. So it has to be two categories though. It has to be two. So I couldn't say find the probability that in these 10 trials that I get a king. If I'm going to draw a card, I get a king, an ace, or a jack, something like that. I can only have two possible outcomes for each trial: success, failure. So things that I can't say that there's no card things that would work. Like I could say I draw a king or I draw a face card. Even though there's multiple face cards, the outcomes would then be I draw a face card or I don't draw a face card. So it still could be binomial, even if there's more than one way for something to happen. It's just that there has to be two specific categories that we're going to group the outcomes to. Alright, and then the probability of success has to stay the same for all trials. So if we're going to use cards, we have to have replacement. Otherwise it has to be something that from trial 1 to trial 2, the probability of whatever we're deeming a success doesn't change from one to the other. Okay, if those four things happen, then we have a binomial distribution, and we can use these properties we're going to talk about. Alright, so determine whether this is a binomial experiment, and if it's not, tell why it's not. Which one of those four things breaks down. So this is a similar example to something you'll see in your homework. So 4 cards are selected from a standard 52 card deck without replacement. The number of 7s selected is recorded. So the two things there, there are two outcomes is there because we get 7s or we don't get 7s. So that's okay. But the fact that we're doing without replacement is a problem, like I said with the card scenarios. So it's definitely not yes, because it's not binomial. Okay, the four criteria are not satisfied. We are going to do it a fixed number of times. We're doing it 4 times. Alright, there's not more than 2 outcomes. There's 7 and not 7. But here's the problem. The trials of the experiment are not independent. Okay, from trial to trial, if I get a 7 on the first one, the probability I get a 7 on the next is no longer 4 out of 52. Now it's 3 out of 51. So it's a different probability from one trial to the next. So that's the thing that suffers here. Alright, determine whether the given procedure is a binomial distribution. Same thing. Surveying 200 college students and recording their favorite TV show. Okay. Alright, so this one, again, it's not binomial. And what is it that breaks down? There's more than 2 possible outcomes. Alright, there's more than 2 possible outcomes for each one of these trials. If you go, Sorry, that's just B. So because of the fact that there are multiple TV shows that people can choose from, you ask a college student, that's considered a trial, asking one of these 200 students, what's your favorite TV show? Well, there's a wide range, not just two things that they can say. Okay, so it's the fact that there's more than two possible outcomes. Alright, multiple choice question. You have four possible choices, A, B, C, or D. Assume that you just completely guess to answer three questions. Okay, so you got question 1, A, B, C, or D. You got question 2, A, B, C, or D. You got question 3, A, B, C, or D. Okay, so use the multiplication rule to find the probability of correct, wrong, correct. So meaning you got this one correct, you got this one wrong, you got this one correct. Just that one specific outcome. Well, how many ways is it to get this correct? There's one correct answer out of 4 possibilities. So that's 1 out of 4 chance. Times, how many ways is there to get this one wrong? Well, there's 1 correct, there's 3 wrong, so that's a 3 out of 4 chance. Alright, and then how many ways is there to get this right? Same as 1. There's 1 out of 4. Alright, and it's multiplication. Why is it multiplication? Because it's correct and incorrect and correct, or correct and wrong and correct. So it's multiplication, so 1 times 3 times 1 is 3, and then 4 times 3, or 4 to the third, is 64. So there's a 3 out of 64 chance of this happening if we're completely just guessing at random. Okay, now beginning with that, we've already done that one. We've already done correct, wrong, correct. Make a complete list of the 3 different possible arrangements of 2 correct and 1 wrong. So I could get correct, wrong, correct. Alright, I could get wrong, correct, correct. Alright, or the last possible outcome would be correct, correct, wrong. That has 1 wrong and then 2 correct. Alright, and then find the probability for each of these. Well, we've already done this one. This one was 3 out of 64. But this goes back to just what there was an example that a student had me do in the last section. Very similar to this. Wrong, the probability of wrong is 3 out of 4. The probability of correct is 1 out of 4. Again, if we're just guessing. So what does that end up being? 3 over 64 again. Alright, and then same thing here. I get a 1 out of 4, a 1 out of 4, and there's 3 ways to get it wrong out of 4. So that ends up being 3 over 64. Alright, find the probability for each one. They're all 3 the same. So as far as probability goes, it doesn't really matter where the wrong answer took place, whether it was the first question, the second, or the third. It's just how many ways are there to get 1 wrong if there's 3 questions. Alright, so this one says how many ways are there to get 2 correct when there's 3 guesses, or what's the probability of that happening? Well, it's 3 times, again I'm going to show you just like I did on that other example. There's a 1/4 chance of getting it correct. There's 2 that we're getting correct. 3/4 chance that we get it wrong, and there's 1 that we get wrong. Okay. And now again, I don't need to put that there, but I just wanted you to see there's 1/4 to the second power. All right, 2 1/4 in all of these. All right, the 3/4 only shows up once in all of these. The 2 means we're getting 2 correct. The 1 means we're getting 1 wrong. And then this 3 is how many ways are there for this to happen. Alright, so I'm going to do it on a calculator real quick. That's 3 times 1/4 squared times 3/4 So I get 0.1406. So 0.141 to 3 places. So not a huge chance of this happening, not a rare event by any means, but definitely not like a majority of the time. But what I want you to get down, what I want you to understand is this 3. Where does it come from? How do we compute it? It's actually 3 choose 2. It's actually 3 choose 2. We have 3 questions, 2 of which we're going to answer correctly. So 3 choose 2, 3 goes here, well, 3 choose 2, and then 1/4 to the second power, and then 3 minus 4 to the 3 minus 2 power. Alright, that's where this is coming from. Alright, and that gives rise to the binomial distribution. So if you read this along, if each trial of event X has 2 disjoint outcomes, which is a criteria for the binomial distribution, we call it success and failure. That's the 2 disjoint outcomes. And suppose the probability of success is P and the probability of failure is Q, and then Q is 1 minus P. Okay, because of this joint, if P doesn't happen, Q must happen. Right? If Q doesn't happen, P has to happen. So that means that they're complements, and so that's how we define Q. Alright, if the given procedure is repeated n times, that's the number of trials, then the probability event, it should be event, X occurs X times is given by this. Now, this is the event. Alright, whatever the event is. Alright, let's say it's I'm rolling a die and I'm going to see how many 5s I get. Okay, I roll. So the event would be I roll a die and get a 5. Right, now the number of 5s I get is equal to whatever this little number is. So let's say if I roll it 10 times, I'm going to see how many 5s I get, and I get 3. Alright, so that's the number that's the number of what outcome we're looking for, and how many trials we're going to do, and this is how many specific successes we get out of those n trials. Okay, so what we talked about on the last slide is this tells me how many ways to get X successes. In n trials. So if we run n trials, the number of ways that we can get X successes is NCX. Okay, so like we talked about on this one, if we run 3 trials, have 3 kids, or sorry, 3 questions on the test, the number of ways we can get 2 right is 3 choose 2. Right, that's what I'm saying right here. Okay, this is the probability of success, and I have X successes. So the probability of success X times. This is the probability of failure. How many failures do I have? Well, if I have n trials, X of them are successes, then n minus X of them are failures. So that's the number of failures. And if you think about it, this is a very, very, very straightforward formula. There's a lot of formulas in math that aren't necessarily straightforward. This is not one of them. This is very straightforward. This is how many ways I can have this happen, how many ways I can have this many successes. This is the probability of success to the number of success power, because we're multiplying everything. And this is the number of the probability of failure to the number of failures power. So it's a very straightforward formula. Alright, so this wants me to do binomial. It wants me to plug into this formula, alright, and answer this. Alright, so I'm going to bring in here, so we'll have it. So we're looking for the probability that the number of successes is equal to 6 if I have 6 trials. So plugging in, I get 6. Alright, I'm plugging in 6 for n and 6 for x. So 6 choose 6. times P is 0.7 to the x power, x is 6. Alright, and then times Q is 1 minus P, so Q is 0.3 to the n minus x, 6 minus 6, so that's the 0 power. Alright, and then you can do this one at a time if you want. I mean, you can do it all at once. Remember, if you're going to use this, you have to use the first number first, then press math. NCR is option 3, alright, and then 6. Alright, there's one way for that to happen. Choose all 6. Okay, so this is equal to 1. Alright, anything to the 0 power is equal to 1. So that part's equal to 1. So this is the only place where you're getting any numbers that are different than 1. So 0.7 to the 6 is your answer. Alright, 0.118 to 3 decimal places. Alright, but I do want you to see that, you know, if your numbers are different, you can put in exactly how you see it. Meaning I could put in 6 math NCR 6 times 0.7 to the 6 power times 0.3 to the 0 power, hit enter, and I get the exact same thing. Okay, so you don't have to do it one piece at a time. You can do it all together, all at once in your calculator. Okay, it's just those 3 different pieces. Notice in between the times symbols, multiplication symbols, I have the 3 pieces that make up this. Alright, and then this one is a binomial distribution. I just want to show you where these values are coming from. If n is equal to 5 and p equals to 0.4, I just want you to see that these are correct. So if n is equal to 5, that would be 5 NCR, and then if I did 0, right, p is equal to, so times 0.144 to the 0 power, that's how many successes, times 1 minus 0.44 is 0.856, and that would get raised to the 5 minus 0 power. Right, 5 minus 0 is 5, so that gets raised to the 5th. So that's where their number's coming from. Okay, and then I can hit, nice thing about this, I can hit second enter, bring back the last thing I just did, and just change these exponents. So I can change this from a 0 to a 1, change that from a 0 to a 1. Alright, and then this exponent and this exponent have to add to 5. Okay, so I'm going to go down here and change that to a 4. Okay, as this goes up, this will have to go down, and vice versa. So 0.3866. So just so you can see that that's where that table is coming from. Alright, and this says find the probability that at least 4 of the subject experienced headaches. So at least 4, what satisfies at least 4? 4 and 5. Okay, only those two. So 0.0018 plus 0.001. Oops, 0.001. Alright, which is 0.0009. 0019, sorry. Okay, so that's just adding up the numbers on the table, okay, and understanding what at least 4 means. But I did want you to see where this thing comes from. Alright, now the TV show Lindsay and Tobias recently had a share of 15. That means that 15% of all TV sets were tuned into that show. Assume an advertiser wants to verify this 15% share by conducting its own survey, okay? And they do a survey with 25 households to begin with. Alright, find the probability that none of the households are tuned into Lindsay and Tobias. So what we're going to do on a problem like this is we're going to use this, we're going to assume that 0.15 is going to be our value for P. Alright, when I'm talking about N, P, and X. Okay, and we're going to do 25 households, so that means that that's N. Okay, but then the X value is changing here. So right now, in this problem, x equals 0. Alright, so I would use NCX, which is again going back to this NCX. That's what I'm using right here. Oops. So I would use 25, choose 0, and then the probability of success is 0.15. So 0.15 to the 0, and then 1 minus p would be 0.85 in this case, and then all 25 people would in the sample would not be watching it. Now don't think just because 0 is involved that we're going to get multiplication to 0. Remember, 25 choose 0, 0.15 to the 0, those values are going to be equal to 1. So you know, still work it out. I'm going to put it in here. That will give me times, but I just want you to see it all separated. And then parentheses 0.85 to the 25. Alright, so 0.017 to 3 decimal places. So we are getting some probability here. So again, these values that contain 0 are actually equal to 1, not 0, so we are going to get something here. Find the probability that at least one household is tuned in. Alright, remember, at least one is 1 minus the probability of none. Alright, we just found the probability of none. So 1 minus that. So that would be 0.983. So there's a 0.983 chance that at least one household is tuned into it. Alright, find the probability that at most one household is tuned in. At most one would be the probability of none, 0, or 1. Alright, at most means that number is the biggest, and go from there all the way down to the smallest possible value. So we already know the probability of 0 is this. Now we have to add to that the probability of 1, right, which would be 25, choose 1, 0.15 to the first, and 0.85. Remember, these two numbers have to add up to the total, so this would be a 24 up here. So I'm going to move this over. I'm going to hit second enter, bring back the last thing I just did, and I'm going to change that 0 to a 1. I'm going to change that 0 to a 1, and I'm going to change that 25 to a 24. Alright, so I get 0.076 to 3 decimal places. Alright, and then I have to add that 0.017 to it because it's one or the other. Alright, so 0.093 to 3 decimal places. Alright, now I'm going to show you a couple different ways. Oh, let me just answer this one first. Does it appear that the 15% share value is wrong? No, this is not a rare event. So if at most one household is tuned in, that's not a rare event in this case. So that doesn't imply anything about that 0.15 being wrong. So if this had been something like 0.00093, and in our data that we collected, at most one household is tuned in, then that would indicate that there's something wrong with that number. Alright, if we get a rare number here, if that does happen to be the case, then that would imply something's wrong with that number, that share rating that they're getting. Okay, but let me go back to this. I want to show you a couple of different ways to do this. On your calculator, even though, I mean, you've got this shortcut button on your calculator. There's an even shorter way to do this on your calculator, and that's the binomial PDF problem. In fact, I'm going to just show that as a different video.